Hello learners, just give me one moment. I'll see if I'm online. Alright, so welcome back to the session. So in today's class, what we're going to see is we're going to quickly see what is Gauss's theorem, and we're going to see one of the applications of Gauss's theorem. Right. So before we begin, my name is Mohana. I'm a physics educator here at Unacademy. And this is the link to the Telegram channel, to my Telegram channel, so you can follow me in this on the Telegram channel, and also this is the common ICSE and ISE board Telegram channel, so you can follow this channel as well. Alright, so just give me 1 second. Let me quickly check if I'm online. Okay, hello. And let's see, okay, let's begin. So before we go ahead, first let's see what is area vector. Let's say we have a surface. Let's say for this particular surface, if you could draw a perpendicular to this particular area over here, right? Perpendicular to the area basically gives you the direction of the area vector. Alright, so if this area is ds means, then area vector ds vector can be given in terms of its magnitude and its unit vector n cap. Alright, so unit vector n cap again will be in the direction of this the area vector. Alright, so any area, if you see, if you could draw a perpendicular to that particular surface, right, that gives you the area vector. Alright, now let's see what is electric flux. So okay, now let's say we have an electric field lines going in this direction. Let's say okay, alright, let's say we have a plate over here, and let's say we have actually connected it to a battery, right? So this plate would be positive charged, and this plate will be negatively charged, right? So field lines would always start from positive charge and ends in the negative charge. So this would be the direction of the electric field line. So in such a field, right, let's say this is the direction of electric field, and over here, if you introduce an area perpendicular to this field over here, then what we have is, and if you could measure how much field lines are passing through this given area over here, right, how much field lines are passing through the given area, then that gives us the idea of the electric flux. Alright, okay, and let's say this is the area, and first point we need to notice is for this particular area, if you draw a perpendicular to the area, right, so this gives you the area vector. Okay, so this gives you basically the area vector delta S, right, and let's say in this case the electric field lines are going in this direction, right. So the red line over here, that represents the electric field, right. So this is basically the electric field. So now if you want to see what is electric flux over here, so electric flux through this particular area will be nothing but how many electric field lines are passing the given area. Okay, now if you see over here, the electric field vector as well as the area vector are parallel to each other, right? So basically the angle between them is 0, but that won't be the case in most times, right? So if you take an area, there is a complete possibility that the area vector, if you see, is perpendicular in this direction, right? This gives you the area vector, but look at the direction of the electric field, right? So the electric field with respect to the area vector, if you look at, there is an angle between them, right? In such a case, okay, such a case what we do, okay, let me quickly finish electric flux and I'll give you the explanation of an electric field. Alright, so over here what we do over here, electric flux is nothing but for a given area how much electric field lines are passing through, right? So what we do for this particular surface, we end up taking a normal, and if you take that normal, that gives you the direction of the electric area vector over here. Okay, this is the area vector, so delta S. Now in this case we are saying the direction of the electric field lines in this particular case are in this direction, right? So let's just take one such electric field line, and if you look at the angle the area vector makes with the field over here, this is basically theta. Now in this case what we are going to do, let's see, we are watching this particular surface from here. Okay, so if you are watching the particular surface from here, then we are not looking at the entire electric field, we are only looking at the component of the electric field that's in our direction of view. right? So what we do, we actually resolve this electric field into its two component vectors. One is along the vertical, okay, then along the horizontal over here. Now what we do, we end up taking what is the field area vector, what is the magnitude of this particular electric field over here, right? So this gives you the area vector, sorry, this gives you the electric field along the direction of the area vector, right? So to obtain this, what we can do, we can take cos theta, right? So if you take cos theta is nothing but, okay, let's say this surface is the horizontal, this is the, let's say this is Ex, that is the horizontal field of the horizontal electric field, right? Horizontal component of the electric field, okay? So cos of theta will be E of x divided by the hypotenuse of this particular triangle. If you take, that is basically E, okay? So this is based on the assumption that we have another component Ey, and that component can be moved to this direction over here. And if you see, we have a right angle triangle, and from here if you want to take cos theta, you will get electric field, okay, the horizontal component by the field over here, okay? Vertical component doesn't contribute to the electric field in this case over here. Alright, so cos of theta is what? Ex is nothing but E cos theta will basically give us Ex over here. So the value of Ex in this case is basically E cos theta, right? So if you see, we basically, if you are watching this particular area from here, we end up seeing the area vector and the component of the field normal to this plane over here, right? So that is the component of the field that is in the direction of the area vector. So normal component of E, that is E cos theta into area, right? That gives us the electric flux through this particular surface. So what we have, E delta S cos theta. E delta S cos theta, this is nothing but your dot product, okay? So E dot ds is nothing but electric flux, okay? Now this gives us the direction of electric flux, and very simple explanation before we go ahead with the new units. Let's see what is the definition of electric field, okay? Let's say we have a field, let's say we have a positive charge. So this charge, we know that it's going to have field everywhere around, right? There is going to be a field everywhere around, okay? Now we want to know at some point over here, we just want to know if there is a field that exists around this particular charge, okay? For that, what we do, we end up introducing a test charge, okay? Test charges are always positive unless otherwise specified, okay? So let's say this charge over here is the source charge Q. So the test charge you introduced is Q0. So this is a positive charge. This also is a positive charge. So what happens? Obviously, this charge would experience a force, okay? This charge would experience a repulsive force. So this charge will be repelled in this direction, right? This is the force. This is the direction in which the repulsive force it would experience, right? So electric field, if you see, is nothing but what is the force experienced per test charge over here. Okay, now what would be the electrostatic force between these two charges? That is very simple. Electric force according to Coulomb's law will be 1 by 4 pi epsilon naught Q naught divided by R square, the whole of this divided by Q naught. Okay, so if you divide by Q naught over here, so obviously this Q naught we can bring it to the denominator over here. Okay, Q naught cancels, so we finally have electric field which is nothing but 1 by 4 pi epsilon naught Q divided by R square. This is for a point charge, for one single charge. Okay, I hope the electric field definition is clear. So if you see what is the unit of electric field from here, electric field has a unit F by Q, right? For electric field unit again, force by charge. Force is nothing but Newton per charge. So force per coulomb. So the unit of electric field is Newton per coulomb. So if the unit of electric field is Newton per coulomb means, okay, then okay, just a second. All right. So if the unit of electric field is Newton per coulomb means, okay, then over here what we have, here we have electric flux. The unit of electric flux will be Newton per coulomb for electric field, and for SI unit for area is basically meter square. So we get Newton meter square per coulomb. Okay. Or if you see electric field, again you can define by electric field can be defined with respect to potential difference as well, right? So from there, if you see for electric flux, again we end up getting a unit of volt per volt meter. Okay, this is very simple. Why? Because electric field, if you see, another way to represent this would be potential per the distance. Potential is nothing but volt per meter you will have, right? So flux when you're taking unit of flux, you will end up having volt per meter into what is the unit of the area over here, that is meter square. So square and meter gets cancelled and you end up getting volt per meter. Now, though flux is basically a product of two vectors over here, okay, what we get is a dot product. So flux is basically the electric flux is basically for a given area how many field lines are passing through, that is electric flux, right? So electric flux is a scalar quantity. Alright, so now the next question, so if you know the answer you can give it in the chat box. A static charge produces what? Only electric field, only magnetic field, both electric and magnetic field, or none of the above? Okay, so if you know the answer you can give it in the chat box. Okay. Okay, alright, so here if you see static charge when you're taking, that is charges at rest, if you see whether it's a positive or a negative charge, the positive charge means its electric field lines will be pointed radially outwards, negative charge means its field lines will be pointed radially inwards. So a static charge produces only an electric flux. Okay, so now that we know what is a static charge, let's see what is Gauss's theorem. Till this point, whatever we saw, that is for an electric field definition also, we saw it for a point charge. Okay, so what if in case you end up having charges that are continuous? Okay, what if you end up having a continuous charge distribution? That is when Gauss's theorem is helps us a lot. So it just gives us a relationship between what is the total flux through any closed surface, okay, and the net charge enclosed within that particular surface. Alright, so Gauss's law just gives the statement that the total flux through any closed surface. So we have a charge and there is basically a closed surface around this particular charge, okay, and the total flux that is passing through this particular charge. So let's say this is a positive charge, so the field lines are going to be pointed radially outwards. So how many field lines passes through this particular closed surface over here? That gives us that charge, that gives us the total flux through this surface, right? How many electric field passes this given area? That gives us flux. That flux is equal to Q by epsilon naught, that is charge times 1 by epsilon naught permittivity of this particular medium. Okay, this gives us the total flux, this gives us basically the Gauss's theorem. Okay, so one more point to be noticed over here. Let's say in case we end up having a irregular surface, okay, let's say there is an irregular surface and there is field lines passing through every point over here and this irregular surface over here. Okay, now what we have to do is, for this particular irregular surface, take a very small portion of it. Let's say the total surface is S. Take a very small portion of it. Let this be ds. Okay, now take a perpendicular to this surface. That is basically nothing but your area vector. So this is ds vector over here. Okay, and this is nothing but your E vector. That is electric field. The angle between them is basically theta. Okay, now if you see if you for this entire surface, if you take each surface over here as a small element ds, okay, and if you could find what is the angle between the area vector and the electric field, okay, then if you see the total flux through the surface will be nothing but integrate over this closed surface S, okay, E dot ds. This gives you the total flux, okay, this is through a closed surface, right? This gives you the total flux passing through this particular surface, right? So here what we have, what is the total flux passing through this closed, what is the total flux, that is E dot ds is equal to Q by epsilon naught. That is Gauss's theorem statement, okay, and it's very helpful when we actually do linear charge density, when you try to find out what is the electric field because of continuous charge distribution. Now let's do one more question. So if you know the answer you can give it in the chat box below. 4 charges plus 7 coulomb, minus 19 coulomb, plus 13 coulomb and minus 1 coulomb, they are all kept inside a closed surface. what will be the outgoing flux through this particular surface? So again, if you know the answer, you can give it in the chat box. Okay, so here what we know according to Gauss's theorem, what we know, total flux through the surface, through a closed surface, is nothing but Q by epsilon naught. Okay, so what is Q over here? Q, the charge over here, right? Let's say we have a surface and inside that we have 4 charges. Let's say this is, inside this we have 4 charges. Okay, let's say 7 coulomb, minus 19 coulomb, plus 13 coulomb and minus 1 coulomb. Okay, so charge or in a particular surface, if you see, right, charge has an additive nature. So the total charge enclosed by the surface will be sum of all these charges. Okay, so we have total charge is nothing plus 7 coulomb, right, minus 19 coulombs, and then we have around plus 13 coulombs and minus 1 coulombs. So the total charge, if you see, this is around 7 plus 13 is 20 coulombs, minus 19 minus 1 is minus 20 coulombs. So total charge becomes 0. If total charge becomes 0 means flux through the surface becomes 0. So flux through this through this particular closed surface ends up becoming 0. Alright, now we have a thin infinitely long straight wire. Okay, what type of distribution will such a long infinitely straight wire would have? Okay, there are basically 3 types of distribution: volume charge distribution, surface charge distribution and linear charge distribution over here. So in this case, if you actually look at, okay, a thin infinitely long straight wire always has a linear charge distribution. Okay, now what is charge per unit length? Alright, let's say we have a wire and there are charges everywhere in this particular wire, right? How charge per unit length of the wire, how much charges are there? Okay, that basically gives us the idea of whether what is charge per unit length. Is it volume charge density, surface charge density, linear charge density, or none of the above? So this is basically linear charge density. Okay, so linear charge density is basically when the charge distribution is along a one-dimensional curve or line in space. Okay, so let's say we have a wire. Let's say in this case there are positive charges. Let's say there are let's say the total length of the wire is L. Okay, the charges in it is basically Q. So linear charge density at any point, okay, linear charge density is given by lambda. Okay, so if the total charge is Q and the total length of the wire is L, means, okay, for a very small region, let's say this is dl, and how many charges enclosed in this very small surface will be dq. So linear charge density will be nothing but charge per unit charge per unit length. Okay, dl by dq, or in other words, if you want to say how much charge is there per unit length. Okay, so if you say this, if you take this total wire that we have taken as unit length, means then it's very simple. How many charges are there in the unit length of wire we have taken? And if the units are very simple, so here we have charge, so this is coulomb, and the unit of length is basically meter, so coulomb per meter is the unit of linear charge density distribution. Okay, now let's do one application based on Gauss's theorem. Okay, so very simple. Till now we have done for point charges, right? If you have a point charge, okay, let's just say you only have one single charge over here. So we know how to find at a particular point, we know how to find the field. Now if we have a dipole, okay, that is, let's say this is 2 coulomb, this is minus 2 coulomb, then what we have is equal charge separated by a distance, then we have a dipole. Obviously for a dipole also we found, we did find what is an electric field, it is easier. But what would happen when you have a continuous charge distribution like this, right? So when you have a continuous charge distribution like this, you can no longer use Coulomb's electrostatic force or the electric field derived for a point charge. You will not be able to use. Why? Very simple. Let's say that we have charges over here. Okay, there are n number of charges. Let me introduce a test charge over here. Okay, Q0. Now, if you try using the superposition principle, what will happen? You have to find what is the field between these two charges, these two charges, and then add all of them together. This process is extremely complicated, right? And it basically makes the whole math itself very much complicated, right? So to avoid this, in this case, Gauss's law comes into picture. Okay, now let's take a charge over here. Let's take a linear charge. Okay, we have a wire, and let's say there are charges everywhere on this wire. So one more point to be noticed here is, let's say we have a charge, okay, and this wire contains charges in it, means, okay, positive charges in it, means the electric field, if you see, will be everywhere around the charge, right? Because of this positive charge, the electric field, if you see, at all points, if you look at, it will be everywhere around this particular line. But I have shown only 2 lines over there, but at only 2 surfaces, but if you see, it is there everywhere around this particular length. Okay, so this is basically how the electric, so if you have a field, there is going to be electric field lines everywhere. Okay, everywhere around this charge, there is going to be a field line. Alright, now if you see, because these are positive charges, okay, because these are positive charges, if you see the electric field lines, if you look at, they are pointed radially outwards. Okay, now if you take a particular distance away from this wire, right, let's go equal distance on both sides. Let's go 1 millimeter on this side, for example, not 1 millimeter, let's not give it a unit, let's say 1 unit, okay, any unit that we are taking. Let's say we go 1 unit on this side, right, and 1 unit on the other side, right, then electric field lines are actually at this point, and electric field lines at this point will be same. So at this point, if the electric field lines is around 5 Newton per coulomb, means this side also it will be 5 Newton per coulomb. Okay, so at equidistance on both sides of the wire, or not on the both sides, and everywhere around the wire, okay, the electric field lines will actually be the same. Alright, now we want to find what is basically the electric field because of this linear charge distribution. Okay, so let's say the charge distribution in this case is linear charge distribution, so let's take this as lambda, okay, and in this case, okay, we have this as the linear charge distribution is lambda over here, right? Now what we are going to do, to actually understand this, to actually find the electric field, we are going to make use of Gauss's theorem, because Gauss's theorem makes this particular electric field, finding the electric field of this long infinite charged wire very easy. Okay, so for this, to find the electric field, we are going to fit a cylindrical Gaussian surface. Why a cylindrical Gaussian surface? Because the field lines are there everywhere around, right? So if you look at, the field lines are not just on these 2 sides, the field lines are there everywhere around. Okay, so if I fit a cylindrical Gaussian surface, and if we could study, okay, how much electric field lines are passing through the given surface, then we can know what is the electric field because of this wire over here. Okay, so in this case, we fit a Gaussian surface, okay, and let's say this length of the Gaussian surface, let's take it as L, and let's take the radius of this cylindrical Gaussian surface, let's take it as R. And Gaussian surface is a hypothetical surface, right, and the Gaussian surface has a value, the flux through this Gaussian surface is always, what is the total charge enclosed by the surface, by epsilon naught. Okay, this is what Gauss's theorem gives us. Alright, okay, so we have, this is the total length of the cylinder, and this is the radius of this particular cylinder. Now what we are going to do, we are going to see what is the electric flux through the 3 different surfaces of a cylinder, right? We have the base of this circular surfaces, right? We are going to see what is the field through this particular 2 surfaces, as well as the field through this particular the radial curved portion over here. Okay, so for that, what we are going to do, we are going to look at the total. How does the flux line through all of the surface flows through. So let's take a very small surface. Okay, let's take a small surface over here. Let's say this is this particular surface that we have, right? This surface of this particular cylinder we are looking at, let's call that as delta ds1. Okay, let's call this surface as ds1. So if you see, area vector for this surface will be in this direction. Now in the previous case we saw, if you take an area over here, well, how is the direction of the electric field lines, right? So electric field lines direction is also in the same direction as the field line over here. Okay, so because of this, what we can say, we can look at what is the flux through this particular surface, right? So let's do this one point at a time. Okay, let's see what is the total flux. What is the total flux through this particular surface? So for total flux through this particular Gaussian surface, let's say the cylindrical Gaussian surface, we let this S, right, is actually equal to, is basically this S is equal to, right, E dot electric field term, how much electric field lines are passing through this given surface, right. But if you look at how much electric field lines are passing through this given surface, this we can divide it into, right, E dot surface 1, that is for this hollow part that we have taken, right, this long cylindrical surface that we have taken, this is surface ds1, okay. What is the flux flowing through this particular surface ds1, meaning if we could know what is the flux flowing through this particular small ds1 surface over here that we have taken, and if we could say this surface over here is made out of such small elements, okay, ds1, then if we can integrate over the surface, we will get total flux through this particular surface over here, right. Now the next surface we are taking is basically at the top of this, okay, at this top of the cylinder over here, right. Let's take a surface over here. So if you take a surface as ds2 over here, right, now area vector will be in this direction, okay, and look at the field over here. Field from here, if you see it has a positive charge, means field over in this case will always be pointed radially outwards. So this is the direction of the field, okay, and if you see, this is the direction of the area vector, that is ds1 vector we have taken. Alright, so for the surface 2, right, we have three surfaces, surface 1, and this is surface 2, and this is surface 3, okay. So this value plus integral, okay, closed integral over the surface S2, right, then we have E dot ds2 over here, plus for the third surface again over here, what we are going to do, we are going to take another small surface, right. Let's say in this case, let's take this particular surface, and area vector for this is going to be in this direction, ds3 is going to be in this direction. Again, think about the direction of the electric field lines in this case. The positive charge is here, the electric field lines will be directed along this direction. Okay, so again for the third surface, again we end up having integral over the surface, closed surface, surface S3 over here, E dot ds3. Okay, now for the three surfaces that we have taken from this initial place, alright, let's basically see, okay, let's basically see what is the flux through the first surface over here. Okay, so first flux through the first surface over here will be E dot ds. This E dot ds is nothing but E ds, magnitude of this is nothing but E ds cos theta. What is theta value over here? Theta value over here is 0 degrees, right? So we have cos of 0 degrees. Alright, then plus the next surface we have is integral over the surface S2 E dot, okay, the magnitude of E dot ds is nothing but E ds2 cos theta, right. But for the surface 2 that we have, what is the cos theta over here? Theta over here is 90 degrees, alright. So we have cos of 90 degrees. This is cos of 90 degrees again. Now for the last surface that we are taking, okay, again if you see, this magnitude of the surface E dot ds is nothing but E ds3 cos theta. Again over here, if you look at what is the angle between the electric field and this area vector, that is actually 90 degrees, okay. Cos 90 is basically 0, so these two terms ends up to be 0. So all we will end up having is basically in this case, all you will have is integral over the surface S1, okay, E ds1, okay, E ds1 into cos of 0 is 1, okay. So E ds1 plus, if you see, this value cos of 90 is 0, then this term also is 0. So we only end up having finally the electric field through the surface S1, okay. Now the electric field and the area vector in the surface S2 and S3 cancels out each other. So the electric field coming out of the Gaussian surface S over here is only because of the region S1, okay. This surface is only responsible, okay, this S1 surface is only responsible for the electric flux, okay, through this Gaussian surface. So electric flux is E dot ds over here. So let's find the value of E dot ds, right. So we have E dot ds, so we have flux is equal to E, right, dot E, okay, we have integrate over the closed surface S1 E ds, right, not E ds, right. Cos of 0 is 1, we have E ds over here. Once again, if you see, right, electric field is basically constant quantity in this case, right, you can take that out. And if you see, integral S, and all you will have is integral S ds. What is integral S ds? Very simple. Integral S ds, okay, gives us the area of the curved surface. Okay, it just gives us the area of the curved surface of a cylinder, right? So what is the area of a curved surface of a cylinder here? Alright, area of the curved surface of the cylinder, that is integral ds, is nothing but it is equal to 2 pi into the radius of the cylinder into the complete length of the cylinder. So if we have a cylinder and if we want to find what is the area of this curved surface that we have over here, that is nothing but what is the length of the cylinder into what is the radius of the cylinder over here. Right, so we have 2 pi r into L. Okay, now according to Gauss's law, what we know, the charge enclosed, right, it's a charge enclosed by a Gaussian surface is actually equal to the flux through the, let's say we have a surface and the flux through this particular surface, if you see, is actually given by Q by epsilon naught. This is flux, this is from Gauss's law, right? Flux through the surface is given by Q by epsilon naught. So we here have Q by epsilon naught is equal to E into 2 pi R into L. Okay, so from here if you see, what do we want? Our final target is to find what is electric field, right? So electric field over here is nothing but it is equal to, we have over here, okay, right, so we have over here Q divided by epsilon naught into 2 pi, right, sorry, just a second, so this will be divided by, right, Q divided by epsilon naught, okay, Q charge divided by epsilon naught into 2 pi R into L, right. But if you see charge per length, okay, if you see what is charge per length over here, right, that is nothing but linear charge density. Linear charge density is nothing but charge per length, right, charge per unit length. So that is nothing but lambda. So we have lambda divided by 2 pi R into epsilon naught. So E electric field, because of this particular linear charge density, if you see in this case electric field over here is inversely proportional to the distance. Okay, what it means over here is very simple. In this case, as you keep going further away from this field over here, the electric field intensity keeps dropping. Okay, so electric field due to a line charge is inversely proportional to distance from the line charge. So E is equal to lambda by 2 pi epsilon naught. So this is actually the significance of Gaussian surface, because for this flux you can simply say flux through any Gaussian surface, it's a hypothetical surface, you can say the flux through that any Gaussian surface is Q by epsilon naught, using which we can equate, we can actually find what is electric field of any continuous charge distribution we have. Okay, so in this case we got E is equal to lambda by 2 pi R. Okay, now if electric field is a vector quantity, so if you want to write this equation in vector form, okay, this area, this distance we are taking, right, this distance vector over here, this R vector, right, you can write this R as a position vector, right. So at what position you are evaluating the electric field, so that we can take it as R vector over here. Okay, so that R vector can be written as R into R cap in terms of unit vector. Okay, so R is a radial unit vector in a plane normal to the wire passing through the point of observation. That is very simple. They are saying R is basically, if you see a wire over here, if you go parallel, okay, if you go perpendicular to this wire, this distance basically gives us R. Okay, so let me end this session with asking a very simple question. So if you know the answer, you can give it in the chat box again. For a line charge like the one we saw right now, the graph between electric field and distance, how would the graph between electric field and distance vary? Will it linearly increase? Will it linearly decrease as we go forward, right? Or will we see a graph like C, or will there not be any change in the electric field lines? Okay, so if you see the graph between, okay, electric field and the distance R, it would follow something like this, the graph shown in E over here, okay, C, option C over here. Okay, that is very simple. Let's take, for example, we got this electric field for a line charge distribution, right, as lambda divided by 2 pi epsilon naught into R, right. E is inversely proportional to R. Okay, for example, okay, for example, instead of lambda, let's substitute instead of the linear charge density lambda, let's substitute the value 5 into 10 to the power of minus 11 coulomb per meter. Okay, let's substitute this value as the linear charge density. Now substitute all the rest of the value, that is 2, we know pi is 3.14, epsilon naught is a given quantity, right? It is a known quantity. So this is 8.85 into 10 to the power of minus 12 into r, right? If you solve for this, you end up getting 8.87 by divided by r, okay? So electric field, so the unit will be in Newton Coulomb. Now let's substitute, let's take a wire, okay? And let's go, let's take this wire over here, okay? And let's say this wire has a linear charge density, okay? So let's say it has a linear charge density. In this case, the charge density is positive, meaning they are the amount of charges in this surface over here is basically q, and if you see the length is basically L. So linear charge density lambda will be the total charges is q by L, okay? Very simple. So let's say the linear charge density, this particular wire has this basically 5 into 10 to the power of minus 10 meters. Now from this wire, okay, first what we will do, we will go 1 meter, okay? When we go 1 meter, we want to see, okay, at all direction 1 meter from this wire, okay, we want to see what would be the electric field, okay? So so in this case the electric field would be around 8.87, right? Now what we are going to do, from this field line over here, we are going to go 2 meters, okay? So when we go 2 meters, what is the electric field? We find it is half of the initial quantity. Why? Because E is proportional to 1 by R, right? Only R is varying, rest all are fixed quantities, right? So 8.87 divided by R is basically 4.47, okay? So we find it to be half of this value. Now again what we do, we will go 3 meters right now and see what is electric field. Okay, so substitute in this equation, substitute R to be 3 meters, you will get 2.25. Okay, again try going 4 meters again, okay? From this field line, what is the electric field strength at 4 meters? You will end up getting 2.21. Okay, so very simple over here, okay? And if you keep going, these are the values you will end up getting for electric field as the distance goes 1 meter, 2 meters, 3 meters and so on. Now if you draw a graph between electric field and distance, see as the graph goes, first initially the electric field at 1 meter, if you see, is around 8.87, but at 2 meters it becomes half of the strength, right? 4.47 somewhere over here. At 3 meters, if you see, electric field lines become 2.96, somewhere around 3. At 4 meters again it becomes 2.20, and if you see, it keeps reducing, okay? And here if you see, what do we observe in this case? We are observing electric field is inversely proportional to radius. So that's why we get this curve over here. Alright, so this is all about Gauss's law and one of the applications of Gauss's law, okay? So with this note, I am ending today's class. Once again, if you like the video, please share it among with your friends, subscribe to the channel, click on the bell icon so you'll always be notified when a class goes live. And there are also many free live classes on the Unacademy platform. Every single day we have a class either for class 11 or class 12 free class happening. So Deepak, the question you're asking is for class 11, and I think tomorrow again I think just go to head to the platform on the Unacademy and there would be a free class happening tomorrow. Okay, for class 11 you can just drop in and ask your doubts and I'll be happy to help you there. Alright, okay. Alright then, with this note I am ending today's class, and do check out the free classes, and those special classes are absolutely free and you can attend them as well. Alright, see you all, bye, take care.